Okay, thank you. So feel free to jump in when I give this presentation so that, okay. So basically, this is the outline of the talk. And I basically, because I do not know how many of you are very familiar with DTN, so I'll start with saying a few words about what is DTN, and then tell you about the unique DTN features that we have in our DAPA project and current or near future work. Okay, so this is a nice picture of DTN. Okay, and as you can see from that figure, basically DTN can run over heterogeneous network. It can be a wireless ad hoc network, it can be satellite network. So for example, JPL, they all are doing interplanetary communication using DTN. You can also run DTN actually over wired network, internet, just internet, because DTN protocol is basically an overlay network protocol. And you can also do it over sensor network. Okay, and so what are some typical real life scenario where you think DTN will be very useful? Over there you see that, so say for example, 9/11, everyone knows that when 9/11 happened, the cellular base station basically were destroyed. So basically, and then people were frantically trying to use cell phone to reach their loved ones, etc. It just doesn't, the remaining base station just did not have sufficient capacity. So what happened is Lucent then sent a band equipped with a movable base station there. And so for emergency response things like this, like in earthquake or even some maybe wildfire scenario, etc., you can easily form ad hoc network using some wireless devices. And then in military operations, we all know that when you go to an enemy territory, you don't expect that they will give you free access to their cellular network, for example, right? And so you need to be able to have run like wireless ad hoc network type of things. So what actually triggered DAPA to fund all this DTN project is purely because they have been funding wireless ad hoc network for a while, for many years, okay? And then with real implementation, they bring all the wireless devices to the desert storm, and voila, they found that it doesn't work. And the reason why it doesn't work is if you just look at many of the wireless ad hoc routing protocol that were designed and published, all of them assume that the connectivity is kind of like near perfect, multiple hop, but you still can have end-to-end connection, which totally is not true in a military operation scenario. Often the connections are intermittent and you have limited bandwidth, and of course with wireless device you also have limited battery power. Okay, and the most successful DTN real network running right now is the bus-based network Disseminations that is running at UMass. Okay, and Hearst, yes. Okay, and so again with this bus network, basically they just put wireless devices in the front of the bus, and when the two buses are within their wireless device are within communication range with one another, they can throw packets at one another. If not, then they basically don't have connectivity, right? Okay, so some of the characteristic of DTN is, so all these researchers says that, okay, we need to design some protocol so that it will work in all these scenarios, intermittent connectivity with limited bandwidth and also with limited battery power. Okay, so these are some of the unique goals that they try to achieve when they try to design DTN. The first one is store and forward. Okay, with store and forward, you can provide reliable delivery across path disruption. Okay, typical TCP will not work because TCP you kind of like expect end-to-end connection. With all these frequent disruption, you're not able to get anything out of a web browser, etc. If you don't have end-to-end path. Okay, and the second thing is because they were hoping that this new disruption tolerant networking protocol can run over heterogeneous network. They hope that whatever implementation that people come up with, it presents a set of common API to diverse networking technology. Okay, so see the picture I show you there. You have several kind of like interplanetary network. You have ad hoc network, typically are Wi-Fi, and you have internet. Anything can happen in internet, right? And then you have sensor network. Okay, so all these kind of like, they are just providing some sort of connectivity below. So you want your DTN technology to run on top, doesn't matter what is below. That's why you need to create something called a convergence layer. Later on, I have a protocol stack to show you. Okay. The other thing is this. Okay, is that most of the time, the data that you want to communicate across are highly sensitive, with the exception of campus network. Even campus network, right? So what do you typically do here within Lehigh, within WINLAB when you use the wireless network? When you use the wireless network here, right, sometimes you do stuff that you don't care if people drop on your traffic. Right? Sometimes you do, for example, you book airline ticket, you do bank transaction. All these data are highly sensitive. You do not want other people to eavesdrop, right? So that's why security is very important, especially because this project is funded by DARPA. So they have information that they need to encrypt, and the data needs to remain encrypted until it reaches the destination, and remain encrypted and will only be decrypted when an application that needs that data is run. Okay, and this is good because that way, because wireless device, you can easily get lost, you can misplace it, and so the data remains encrypted. Even if it falls into the hands of enemies, they can't basically decipher the data. Okay, and then the fourth bullet item there is because of the fact that some of their network, their wireless backhaul have very limited bandwidth, very limited bandwidth. Okay, and then they have typical wireless ad hoc network that basically just use Wi-Fi radio. That one has much higher bandwidth than the wireless backhaul that span larger area. And because of that, they need the content to be cached to minimize traffic and latency. And the last thing is, most of what I'm trying to focus on today is that they want to be able to deliver messages in a way whereby it's very different from existing internet. So existing internet, you type a host name, and then you use DNS to look up the mapping between the host name and IP address, and then you send a message. Okay. Most of the time in military operations at that time is that they have no idea who the recipient is, but they have some description of who the recipients of the message should be. So let's say you find high value target. That refers to when you find enemy information, like you find the location of Osama bin Laden, for example, right? And you want to send it to all the captains within certain target region. Okay, you have no idea among the 10 captains that you have who currently is in that target region, right? But so that's why they want messages to be able to be delivered via roles, locate or location description or conjunction or disjunction of all these attributes. Okay, and this is the feature that seldom people talk about when you attend DTN talk. Most of them focus on the routing protocol. Okay, and so this is just for educational purposes. So some of you that are familiar, you can then briefly take a short nap for 5 seconds. So typical traditional TCP/IP connection, you basically need to have an end-to-end connection, and so the end-to-end connection is between the source and destination, and intermediate routers basically just route based on IP address. But you need the end-to-end connection to simultaneously exist, otherwise TCP won't work. Okay, and because of that, in the extreme network environment that I had presented in the first slide, we basically need a new networking protocol such that when there's no end-to-end path, you are still able to deliver, to have message delivery. Okay, and so in DTN technology, basically what you do is this. Okay, you know your destination endpoint description. Okay, you say I want this message to be delivered there. Even though there are no end-to-end connection, what you can do is your nearby neighbor, you can then ask that no, are you willing to be the custodian of this message? What that means is, once I pass you the message, you promise me that you'll try your best to deliver this message to the final destination. Okay? So this is like kind of like hop by hop acknowledgement I give you. You say yes, I will guarantee to be the custodian of the message. Okay? So that way, even if you have, at that time when I pass you the message, even if you have no connectivity to the final destination, that message got stored in some persistent storage. And that guy, when they meet other nodes, etc., they can then make use of context information as to when I meet another node, whether that node has a better chance of reaching the final destination than me. If that's the case, then I'll pass it to you. If not, then I won't ask you to be the next custodian, etc. Okay? Alright, so what are some of the design issues in DTN? Okay, so most of the people only work on this part. Okay, so message delivery, of course, is important, especially when you want to have a protocol that can work without simultaneously assisting end-to-end part. Okay, and so people work on designing unicast DTN scheme, multicast routing scheme. So one of the scheme that we use in our implementation is something designed by UMass Amherst in their Disseminations, something called Rapid. Prophet is another protocol that get implemented. The reason there are tons of DTN forwarding schemes. The reason why I mentioned these two is these two are the real DTN network that are operating 24/7. Okay, so this is deployed by a Swedish group for some of the people that more like live like a nomad in Sweden. Okay, and then of course many papers published on designing unicast and multicast scheme, including us. This message delivery scheme you want to design in such a way that it works across heterogeneous domain. For example, sensor networks, wired internet, etc. And we have a constraint, right? You can either design DTN protocols such that you say, I want to have a clean slate design, doesn't have to consider backward compatibility, you're free to do whatever you want. But unfortunately, since this project is funded by DARPA, they have to put certain constraints that it has to work with existing internet. Okay, so certain design decisions are made because we need to make sure that it operates inside existing internet. And implementation, UC Berkeley started the implementation, so they have a reference implementation. It goes through multiple iterations, and currently I don't know, this is the 2.5 and 2.6 versions are the versions that we use. Europe also have their own implementation. So the most well-known one is I forgot. Ray, do you know how to pronounce his name? York. Oh, is it? York. York. Yes. Okay. So, and then for the intentional naming features, the initial prototypes started by Vivian and us. We did not start off with promising DARPA that we want to implement the intentional naming feature, but because of our security feature, which later you'll understand why, we ended up doing it for DARPA. Okay, and that is kind of funny because during the end of phase 2, both only Vivian and us were on this, and then everyone get excited. So my phase 3 SRI also joining, Xerox also joining, and of course the other issue is the security design. Okay, now the thing is this, most of the people when they design network security, they keep on. So if Cisco is trying to sell product to DARPA for DTN, Cisco can try to say, hey, you can still use IPsec, no problem, etc. Right? But that doesn't meet DAPAs made because DAPA wants something that when I cross different domain, I don't have to call everybody to coordinate what IP set security, how to configure, etc. Okay, and so later you'll see how we provide the solution. Okay, so our phase 3 goal is that we want to provide data-centric security solution. So we want to design a solution that provides the following features. Okay, key management costs should be independent of the total number of data subscribers. Okay, by data subscriber in this particular scenario, it purely means that those users that are interested in certain piece of information. Okay, and each data subscriber can decrypt the item that he or she is interested in as long as he or she has the right authorization key based on his or her assigned attributes. And we need to implement this, and we also need to integrate it with the intentional naming feature. Okay, and we also implement the inter-domain routing scheme and integrate the whole feature. So let me focus on what we meant by intentional name delivery or the late binding feature. So typically, a DTN EID looks something like this. Okay, you say disseminations.umass.edu//bus1. So if you want to send a unicast bundle, you just say, I have my own source DTN EID. This is my destination EID, and then the underlying DTN forwarding scheme will forward a message for you. Okay, but we want to be able to do this. Okay, we want to be able to say that I want this message. I don't know who the actual recipient is, but I want this message to be sent to within 200 meters of this particular center. So it's a target region, and to all the users there that has an attribute that say that I am a captain. Okay, so this message is meant for all captains within the target region area within 200 meters away from center location 13. Okay, and not only that, I want to be able to do conjunction and disjunction of some of these attributes. So say, for example, I'm in the Allentown location, and where there are different representatives from different companies were there, and I say that I want this message to be picked up only by managers within this target region, or all the employees that belongs to company A. Okay, so this is kind of like conjunction or disjunction. You'll be able to do that. Okay, so how did I implement this intentional naming delivery feature for them? So I mentioned to you that we want to be able to work across heterogeneous network. That's why you have a convergent layer here. But we didn't try anything related to sensor network. And then this is something called the bundle protocol agent. And this is the data store where you can store your data bundles, and these are some DTN application running. So this part is the interesting part. And so you have an external router. The reason why you want to implement something, an external router, is you can have zillions of routing schemes. So you want to implement it in such a way that if you don't like this routing protocol, you take this piece out, you plug in another routing scheme, etc. Okay, and so I'm going to describe to you what happens. So let's say your application, you have a query. The application say, I want to send a bundle to all captains within this location, this region, right? And then that got forwarded to the bundle protocol agent. It will then send a kind of like a broadcast message to say bundle event received, and the external router will be able to pick it up, and then it will pass the intentional name, and then go to the resolver to say, tell me this corresponds to what? How do I route to the next hop? Okay, and this guy will dig into the knowledge base that you have and come up with some answers for you. Okay. Later I'll kind of describe. So the intentional naming resolution doesn't happen immediately that I pass you guys all the IP address of the guys that need to receive. Okay. Afterwards, there's an example that will make this concept clearer. And once I get that, I will then find out which link I can send it out, send the bundles out, and then send it out through the convergence layer. Okay. Same thing if, let's say, I receive a bundle, I come in, and again, there will be an event that say event bundle received, and I again go through the router to determine whether this bundle is for me. If it is for me, I pass to the application. If it is not, this process will again tell me how to forward it out. Okay? Alright, so this is the example that I promised you. Okay, so let's say that I say I want a bunch of PhD advisors were meeting in a certain area, and I plus their student, and I say I want this message to be picked up by all the advisors within 100 meters of building A. Okay, so the source first determines the location of building A, and then it routes these bundles to nodes that are within 100 meters of that location. So it may be that initially, okay, I am very far away from the target region. So if that is the case, this message will be forwarded via geographical forwarding to minimize the overhead that I need to use until it reaches the first node that is currently located in the final destination area. Then I can flip my routing into flooding. Okay, this is just an example. Once you reach your target region, you need not use flooding. If you have some infrastructure server that can tell you who exactly has such attribute, then you don't need flooding. Okay, but in our demo, this is basically what we did. Initially, we do geographical forwarding. Once we reach the destination area, we flip it to flooding, and then the nodes with the right attribute will basically pick it up and then pass it to the application. Now, even if the nodes do not have the right attribute because of the fact that we have security, we don't care that much because that guy will simply not be able to open a decrypted message. Okay?
So it seems like there's kind of a two-level phase. Basically, location is the highest priority when looking at all these things. So
okay, this is just an example. You can basically in your reasoner, you can basically say which attribute is more important.
And act on that one first,
yeah.
And then.
Yeah.
Has there been any work on something like an actual resolver that would do something other than just look at location first and then flood out?
No.
That's
what I'm saying. The look at location first is because we only have limited time. So we do it that way. Mm-hmm. So with a reasoner, you can do anything you want. Okay? Alright, so now after I explain to you what is intentional name message delivery, I'm going to kind of describe to you how we did the security part. So in phase 2, we designed a hierarchical key structure based solution for security. But soon, I'll kind of briefly describe what it is. So we assume that we have certain ontologies, and then we use certain number of bits to represent certain branch, etc., and then create some key based on that. But this approach is not good. Why? Because sometimes when you receive a data item, it could belong to this category, it could belong to another category. Okay, so it is not as flexible if I design my security key like that. So instead, we use something called a cybertext attribute-based encryption scheme. So I'm going to briefly describe to you what the cybertext attribute-based encryption do. Okay, it consists of 4 components: the setup, the key generation, the encrypt, and the decrypt. So the setup is very simple. So basically, you feed it with some security parameters, and it outputs 2 keys of information for you. One is called the public parameters. The other one is called the master key. The public parameters later will be used in the encryption scheme, and the master key basically is used in the key gen. Okay, and so inside the key gen, I need to be able to generate quote-unquote private key to each user based on the user's attribute. Okay, so I gave it the master key, plus a set of attributes that this particular user has. So say, for example, this particular user is a captain, belongs to Navy, and could potentially have certain security clearance at a certain level, right? All these are attributes, okay? And then I give this user their private key, and whenever someone needs to encrypt certain messages, okay, it says that this message has a certain access structure. The access structure basically tells you all the attributes, has to match certain attributes before this guy can open this message, okay? And I can encrypt the message based on this and then get my cybertext. With the cybertext, I can shift it out using DTN forwarding. And any node that tries to decrypt it, they need to possess all these attributes. Otherwise, they won't be able to decrypt it. Okay? And I'm not going to go through all the math.
So I have a quick question about, it sounds similar to an identity-based system where you have...
It's slightly different than just simple identity.
Sure, but you do have a private key generator that's distributing keys based on input, right? So how would revocation work in a case like this? Because
very good.
Your attributes...
Can you hold your question? I think I finish this. Very good question, okay? And so the basic scheme that was designed by Gonek, they all does not support negative attributes. So it makes user revocation harder, okay? So our contribution basically is we kind of like change the scheme a little bit so that we can support negative attribute. This example will be clearer in the next slide that I'm going to show you. And the reason why we need a negative attribute is very obvious, right? You can say that this message can be opened by all captains within this region except Captain A, because Captain A is being revoked, okay? And and then the other thing is this, okay? There may be some messages that you will say that I only want those people that are currently in those locations to open it. If they are not in those locations, doesn't matter whether they are captain or not, they shouldn't be able to allow to open it, okay? But users change location all the time, right? So how do you deal with dynamic variables like this? We also change the scheme to be able to handle this, okay? And so this is the example. This is a track thing example. Let's say you have a bunch of professors, advisors, not professors because professors don't get involved in sports team. Let's say football coach or basketball coach, okay? And they have a tri-state sports event and they all go there. And the organizer of the event says, I need to send a message so that this message will be picked up by all advisors within New Jersey State or any team member that belongs to team D, C, D, or E. Okay, so that is the benefit of attribute-based encryption scheme. You specify the access structure, and then only users that kind of like satisfy this access structure will be able to decrypt the message. Okay, but this basic scheme does not support negative attribute, right? So if, let's say I want to say that this message is for all advisors in New Jersey, except advisor from Rogers, then I can just say all advisors, but not from the one from Rogers. Okay? And so I was able to do that. And then dynamic attribute, the way we do this is kind of like create a pseudo node. And then kind of like create another access tree purely based on location. And so that way, once I can verify your location, you get this component, and hence you'll be able to decrypt the whole thing. Okay? So this, basically, the way we design this, of course, I mentioned before that certain design decisions were chosen based on the application scenario that we intend to support. Okay? So in their case, they could have at different locations, you have a Humvee, you have what, right? So they could become your key delegator that allows you to verify the location of the soldiers and give that particular verify that particular component of the attribute, and then give you this component that you need in order to open up the message. Okay,
So I don't fully understand why are negative attributes so different when it comes to handling them than say positive attributes. Like,
well, you just need to define extra structure that is all related to the math. At the end of my talk, I did put some references on the paper. Okay, so if you're interested, you can kind of like dig up.
Just a very, very quick follow-up. With the so and then I'm assuming that you would basically have to prove in some way to the private key generator that you own certain attributes.
No. All this is hidden in the private key that you have.
So how did you get that?
So that's why again these type of things work in military because every time a wireless device is given to a soldier, right? They already know what the attribute this guy has.
right.
So it's already inside the wireless.
So there was a way for that person to
Yes.
initially out of band prove that he owned those attributes in order to obtain
Yes.
that. But how?
And then the dynamic attribute is this. Again, we rely on the fact that in a military scenario, there are some loose hierarchy right. So say for example, if you are the captain, you can use your captain as your key delegator, which means that he owns certain components that allows him to give out certain private key components to the users if that users can prove to him that I can give him this private component.
Sure.
And once he has that private component that is only needed if you happen to have messages that are encrypted with the additional component that is dynamic.
So then with the negative attributes, then if some, say a device were to get stolen and you have to basically revoke, this is a professor at Rutgers, say, the device that got stolen. So you have to revoke, you have to include a non-Rutgers tag. So would all of them have to then get another key in that case? How would the...
But stolen device is unique attribute.
So it's like, right? So as long as so the neat thing about this thing is that if you are not rugged, you don't need that component. The math automatically will work out. Okay? Alright. Alright. So we basically implement our late binding on top of the rapid router, and the only reason why we choose rapid, two reasons. One is we were hoping that eventually we will be able to run it on Ethernet. Second thing is at that time, the only available public domain external router implementation is Reddit, okay? Because Prophet was kind of like the people who implement Prophet basically hack some of the lower layer codes in DTN, which we don't quite like, because then it makes it very harder whenever you want to change or add new features, okay? And so when we need to send all this like access structure, etc. Okay, IETF actually defines some meta extension block. Again, we didn't use that. We kind of like create our own view, etc. Okay, and of course the other thing we need to be concerned about is usually people are concerned about. You say, yeah, you can come up with sophisticated encryption scheme, right? But if such thing doesn't work on mobile devices, then forget about it, right? And so we kind of like have some performance numbers, and later on at the end of the slide. So all our prototype by the end of the data demo are all shown on desktop. But since then, we have successfully implemented on iPhone, okay? And we actually tried all sorts of phone. We started off with Windows Phone, but unfortunately, Windows Phone doesn't support one of the big number libraries that we use, and again because of limited time we didn't bother. And Windows Phone, the problem with Windows Phone most of the time is that they tightly control what you can access, what you can't. So even TCP port, sometimes they don't allow you to just simply create a TCP port. Okay, so for those of you that haven't read the Ethernet, the rapid paper, I kind of like give a brief summary here because I'm going to talk about this when I talk about interdomain routing. So this is how rapid works. When two nodes meet, they exchange some meta information, and then they deliver packets that are destined for to each other. And for those packets that are not meant for each other, what they did is they have something called a utility function that basically can then tell you whether the other node that I need is a better carrier for this message than me. Okay, if it is, then I will replicate it to them. If not, then I will still store that message in my storage, etc. Okay, and since the connectivity between different nodes are kind of like variable duration, right? You may have more messages than you want to send out, so you just basically arrange those messages in decreasing order of marginal utility and try to push as many as you can while the connectivity is still there. Okay, so I'm going to show you our implementation. We have 3 types of nodes: storage nodes, publishers, subscribers. So publishers send encrypted data message. The storage node and the subscriber kind of like retrieve some of these messages from the storage node. Maybe some of you cannot see this too clearly. So here is the GUI that a user can see. So whenever you receive some messages, encrypted messages, it show up there. So a particular user can click, say, I want to see what this message is all about. If he has the right attribute, then this guy basically will say, okay, you can open up successfully, and then display some messages for you. Okay. If that guy doesn't have the right attribute, okay, it will then give an error message to say you don't have enough authority to view this message. Okay, and of course the third message happens not to be encrypted. It's a clear text, so you can see it anytime you want. Okay. And this is the GUI that we have for our late binding router. So basically you can type your message and then you can choose the description of who you want to send to, like company A, so etc. And you can also include location, the center, and longitude, latitude, and the radius, the target region, and then you can hit send. You can actually say you want to encrypt or you don't want to encrypt. Okay, so this is the demo scenario. At that time, because they slam a rule that says that you cannot disclose what you are doing, it's nothing secret, but they say you cannot disclose anything you do to other people not in the project. We can't even use all of it. So all this on the laptop we bring to Arlington to show them. Okay, so this is basically what we show. We have this as the sender, and these 2 nodes have all the attributes that are needed to decrypt the message. This node is added to show that initially is geographical forwarding. Okay, between these 2 nodes that I can hear, I know that this node is kind of like closer to the target region, so I pass it to this guy, etc. Until I hit the first node that basically satisfies the target region. Then it becomes flooding, and these 2 nodes picks up, and this node does not have but assuming that all the nodes are friendly, it will be broadcast, and only these 2 nodes has all the right attribute to decrypt the message. They basically get to decrypt the message. Okay, so this is the picture to show you. We basically encrypt this message at the source and decrypt this message at the end at the 2 nodes that I showed you just now. Okay, so apart from intentional naming and security, we basically also implement some interdomain routing schemes. In phase 2, we basically just do simulation, and we design two protocol. One is gateway based, the other one is ferry based. And of course, in every DARPA project, you need to do some implementation for them. So we basically implement the gateway based approach because at Lehigh we don't have buses that are equipped with wireless devices, even though we would like to try. But it's just too hard because I basically need to kind of like a lot of red tapes. So that's why we decided to implement the gateway base. Okay. So how does this work? It's very simple. You basically assume that different domain, they can run their favorite intra-domain DTN protocol. So you can say one domain run Prophet, the other domain run rapid. Okay, so we assume that the beacons that we send from the beacon, you basically can tell that the other guy that you kill whether it's in the same domain as you or not, just based on the DTN PID. And if you can hear someone that is outside of your domain, you basically send a gateway registration message to your cluster head and say that, can I be the gateway for this domain? Because there could potentially be more than one node that can hear this. So the gateway, the cluster head will basically give you permission, yes, you can be the gateway or not, okay? And then a node within the domain who would like to send some messages to some nodes outside of the domain will basically query the cluster head to say, who is the gateway for this domain, and the cluster head will tell it the information, and so the node can then send a bundle message to that gateway. So because of this, within that domain, you can use the intra-domain routing protocol to forward to that gateway. Once the gateway receives it, he'll open the bundle, he knows who else outside of the domain to pass that bundle to, okay? And then once that bundle reaches the other domain, right, it will basically just use the other domain's intra-domain routing protocol to deliver the message, okay?
So there's no replication between domains? One gateway sending to another gateway, there would be no replication method? Like the method, there would be no DTN protocol that's running between domains. That is, it would have
Yes.
to be gateways. So
Yes.
you're not replicating.
That was purely because at that time we are only doing small scale, okay? And so this basically, we show you that for this particular scenario, we only have two domains. One domain running Prophet, the other domain running Rapid, and we basically show you that I can toss messages from one node within the Prophet domain to the Rapid domain, and this is the reverse. I can send some packet from the Rapid domain to the Prophet domain, and eventually we decided to do the tree domain, purely because we want to show that, so in this particular example that I show you, there is no direct connectivity between domain 3 and domain 1. It has to go through domain 2. Okay? So how does this work? So basically, when this node can hear this, since it registered with the cluster head, anytime the cluster head has updated information, it will send out to all the gateway that you know of, so that this gateway basically are aware of the fact that G1 exists, even though this domain has no direct connectivity with the other domain. And we successfully show this as well. And of course,
But you have to know who is in G1 in order to send that message, right? Some attributes in G1.
Yeah, so you just so you don't have to know the idea.
Yeah, but you need some attributes in G1.
Yes. Okay. And so, of course, just unicast message is not good enough for them. We basically also have to show that the multicast work. And so when we designed the interdomain multicast, initially we just do simulation. But as far as DARPA is concerned, they are not interested in simulation results. You need to implement something to them. And again, we basically use Prophet and Rapid because at that time, those are the two that we, so it's pretty much very similar. The only difference is that we kind of like use something very similar to IP multicast. So this is the demo scenario that we gave. So the source basically send some messages to the custodian node. And let's say R11, R12, and R13 was interested in what S1 sent. Okay, so the custodian basically used the intra-domain protocol to deliver to R11, and it also knows that these two other nodes subscribe to its message, so it will use inter-domain scheme to deliver the message that this guy's broadcast to these two other nodes that subscribe to it. Okay. Same thing. We want to make sure that it's kind of like this is not hard-coded. So we basically also include the second session to illustrate the fact that the reverse direction basically also works. Okay, so like what I mentioned, the demo initially was done, was done in using desktop. We carried seven or 8 laptops to Arlington to show them. But recently we successfully port our software to iPhone after some struggles. So we started off, like what I mentioned, we started off with Windows mobile phone, and then we found that there are many things that don't work, so we basically have to re-implement the DTN stuff to make it work on Windows mobile. And then we found that our security library doesn't work on Windows mobile, so we switched to Android. But even Android, we can't make our security libraries to work, and finally we switched to iPhone, but iPhone we succeed. And we basically, so that project ended, but we got funded by Army Research Lab to do further work on it. And unfortunately, again, they slapped me with this rule to say that you can't tell anybody what you're doing for me. So hopefully, because it's just a 1-year project, so hopefully maybe end of my stay here, I'll be able to tell you what is it that we are doing for them. And this DTN 2.0 reference implementation is very, very heavyweight, okay? And so right now we are doing some lighter weight implementation and also include some new features for our NSF program. Okay, so any questions there?